Welcome back. So last time I mentioned that we were going to do improper integrals, and I accidentally had left that on the title of the last slide. So last time we dealt with volumes. This time we're going to be dealing with improper integrals. And so we've already been sort of wrestling with this idea of infinity in our course. And one of the things that we want to do is, well, we have one kind of infinity, so these infinitesimals. So we've been like shrinking our little rectangles to be as tiny as possible and having infinitely many of them. But we've been dealing with a finite interval, so an interval from a to b, which is finite. What if we want to integrate all the way to infinity? Does that work? What does that even mean? And so that is what really improper integrals are. So these are integrals that go to infinity in some way or another. There are different types of improper integrals. We're only going to deal with one primary type of improper integral, which is when you're integrating where one of your bounds goes to either plus or minus infinity. Come on. Sorry, I am having trouble with technical difficulties. And my slides are not showing up. That is a bit of an issue. Give me a moment. Why is this not working? Okay, that is really quite troubling. Let me get out of this quickly and see if I can get back in and if that'll fix things. There. Okay. So sorry about the technical difficulties, but basically, what happens if one of our limits is infinity? So here, normally, we have both an a and a b, and they're both finite, right? So they're both some real number. In this case, what we're going to have is instead, one of our limits is going to be infinity. So what does that mean? Well, we know how to deal with infinity, right? You just take limits. And so if you take limits, what we're going to do is we're going to take the limit as b goes to infinity from the interval from a to b. And so if you think about it, what we're going to be doing is, if we have some shape here, some shape like this, we have a and we have b. If we keep on moving b over to the right, well, then you keep on getting a bigger and bigger integral. But now, there's some chance that that integral will actually converge to a number. So as you take some limits as you go to infinity go to a real number, and then the improper integral converges. Sometimes they don't, and in that case they diverge. And so that's the basic idea behind integrating to infinity, is you just take this limit as one of your endpoints keeps on going further and further to infinity. You can do the same thing going the other way. So if you have some function like this, and you have your b and you have your a, you can also send your a all the way to minus infinity. And again, if the limit exists, then the improper integral converges. If the limit does not exist, then it diverges. And once we have these two different types of limits, you can also define the limit from minus infinity to infinity. And basically what we're going to do, so initially you might think, oh, well, we just need to set both a and b going to infinity and minus infinity at the same time. But that's a little bit hard to define because that requires you to have two different things, two different limits. However, one of the nice things about integrals is you can break them up, remember? So, converging and diverging. So converging just means that the improper integral is a number. So sometimes when by diverge, I mean that the improper integral, the limit doesn't exist. It's not a real number. So maybe it keeps on growing bigger. So for example, let me give just a quick example. So the limit as x goes to infinity of 1 over x is equal to 0. So this converges because it goes to a real number. On the other hand, the limit as x goes to infinity of x squared, well, that goes to, well, positive infinity, which is not a real number, and therefore it is a diverging limit. Okay, so hopefully that answers your question, Anisha. But yeah, so what we mean here is sometimes these limits actually give you a number. And when those limits give you a number, well, then it makes sense to talk about integrating to infinity because you still end up with a real number. Now, we can also push both a and b to positive and minus infinity, and we are making use of the fact that we can divide up our integral into two different parts, where you're integrating from minus infinity to c, where c is any real number, and from c to infinity. Often, for ease of notation, we let c be equal to 0, but it doesn't matter which c you choose, so long as your functions are continuous. And so, in this particular case, if both integrals on the right converge, then the integral on the left also converges, because you need, well, a real number. So let's give a couple examples, and hopefully that'll make this a little bit more clear. So let's start by giving you a convergent example. So this is the integral from 1 to infinity of 1 over x squared. So this is going to be the integral from 1 to infinity of 1 over x squared dx. So that's going to be equal to the limit as b goes to infinity from 1 to b of 1 over x squared dx, which is going to be equal to the limit as b goes to infinity of minus 1 over x from x equal to 1 to x equal to b. Well, we plug that in. This is the limit as b goes to infinity of minus 1 over b plus 1. And so, well, the limit as b goes to infinity of 1 over b is just 0, right? Because 1 over infinity is equal to 0. And so then this entire thing is just equal to 1. And so this is a convergent example. Let's give a divergent example and see what happens. So here I've drawn f of x is equal to 1 over x. So now here the limit from 1 to infinity of 1 over x dx is going to be the limit as b goes to infinity of the integral from... Oh, sorry, can you go back, please? Yes, please stop me when I go too fast. And of course, as always, these notes will be available after class. But so the basic idea here is we are taking the limit, we're taking the integral as we normally would, and then just substituting in infinity for one of the values. And when you substitute in b is equal to infinity, well then this entire term, this term gets cancelled out, and you're left with just 1. How did 1 over x squared change to minus 1 over x? So that is because the integral of 1 over x squared dx is equal to minus 1 over x plus c. So this is the integral, because if you take the derivative of that, you get 1 over x squared. Yeah, so this is one of the many examples of why you need to be really, really fast at integrals, because you just show up over and over again in these problems. Okay, let me move on to this next example. So we have, this is a divergent example, and we'll see what happens when we take the integral. So this is 1 over b from 1 over x dx. So that's equal to the limit as b goes to infinity of, why isn't it minus 1? Okay, we have a question. Let me go back to the previous one. So why isn't it minus 1? And this is because, well, there are actually two answers to this. One is the area beneath 1 over x squared and 0, is that a positive area or a negative area? So you should, this area here is a positive area, so you shouldn't ever have so you shouldn't end up having a negative integral. But algebraically what's happening here is this is equal to, let me put this over here. So this is equal to minus 1 over b minus 1 over 1. Which is why that's equal to minus 1 over b plus 1. Okay, yep, so let's, moving on. We have this limit, it's the limit as b goes to infinity of this quantity. So what is 1 over x? The integral of 1 over x, that's one of the things that you should have memorized. So this is just the natural log of the absolute value of x from x equal 1 to x equal to b. So this is the limit as b goes to infinity of natural log of b. Well, it's positive, so you don't need to worry about taking the absolute value, minus natural log of 1. Natural log of 1 is equal to 0. So this entire thing is equal to the limit as b goes to infinity of natural log of b. But now, unfortunately, the natural log of b, that goes to infinity. And therefore, this one is divergent, because it doesn't converge to a single number, because you know that the limit as b goes to infinity of natural log of b, that keeps on growing unboundedly. It grows slowly, but it still keeps on growing. and so never reaches a particular number, or it goes past any number. Okay. I have several more examples, which is important because, and I will try to go over them a bit more slowly because I will be making use of some of the techniques that we've learned in the other course, in the other lectures. So let's start with a pretty complicated example. Let's say minus integral from minus infinity to infinity of x over x squared plus 1 squared dx. Okay, so now the first thing we're going to do is we're going to break this integral up into two pieces. So this is the integral from minus infinity to 0 of x over x squared plus 1 squared dx, plus the integral from 0 to infinity of x over x squared plus 1 squared dx. And let's just solve the first half first. We have a question. Is the definite integral from minus infinity to infinity the same as the indefinite integral? No, it is not. So the indefinite integral gives you a function, right? Whereas the definite integral gives you a value. So from minus infinity to infinity, that is the area underneath the curve for everything, whereas the indefinite integral isn't. And if we choose any c instead of 0, will we get the same answer? Basically, yes. So you will, with the exception of some really weird functions that you can't take the integral of anyway, you can choose any other c. But often it's easier to choose. For most examples, it's easier to choose c, at least examples that I give. But yes, you can choose any other value that you want. Because one of the things to remember is if you think about the fundamental theorem of calculus, the integral from minus infinity to infinity, well, that's equal to some function at infinity minus some function at minus infinity, right? But you can set that equal, so this is all heuristic, so this is not rigorous, and there are all sorts of things I'm playing fast and loose with here, but this is equal to f of infinity minus f of 0 plus f of 0 minus f of minus infinity, right? And so you can break it up into these two pieces. And so that's why you can do this sort of breaking up of definite integrals. Let me erase that quickly. But yeah, and you notice that doesn't matter that you're choosing 0 instead of some other number. Just don't choose infinity. If you choose infinity, weird stuff might happen. So, well, I mean, I guess weird stuff won't happen. You just won't be making any progress. But anyway, let's just work on the red part here. So what's the integral from minus infinity to 0 of x over x squared plus 1 squared dx? So now, when you stare at this problem, there are a couple of things you might think. The first thing is that this seems like a more complicated integral, so I should use one of the more advanced techniques. In this particular case, I'm going to use U-Substitution. So I'm going to say that u is equal to x squared plus 1, and du is going to be equal to 2x dx. When I do this turns into the... let me rewrite this as a limit first. A goes to minus infinity of the integral from a to b of x over x squared plus 1 squared dx. And then I'm going to plug in these u's. So this is still a limit as a goes to minus infinity of the integral. Note that when I am plugging in u's, because I'm doing a u substitution, this is a definite integral, I need to substitute in. Here, this was x is equal to a and x is equal to b. Here, u is equal to a squared plus 1, and u is equal to, well, if I substitute in b there for u squared, what just happened there? Oh, that's a 0, that's why. Sorry, that should be a 0. That's a 0, and so u is equal to 1. Okay, because here x was equal to 0 and x was equal to 1, and here we know that u is equal to x squared plus 1. And so we change the limits of integration. And then what is du? Du is 2x dx. Therefore, x dx is equal to 1/2 of du. So this is 1/2 du divided by, well, x squared plus 1 is equal to u, so this is just u squared. Okay, so now we've done this, what we end up getting is this is equal to the limit as a goes to minus infinity of 1/2 times minus 1 over u, because that's the integral of 1 over u squared, from u is equal to a squared plus 1 to u is equal to 1, which is equal to the limit as a goes to minus infinity of 1/2 times minus 1 plus 1 over a squared plus 1. Well, what is a squared plus 1? That's going to go to infinity. So that's going to, this part here is going to go to, that part there is going to go to 0. And so this is just equal to minus 1/2. Sorry, I went into the margins there a little bit. But that's equal to minus 1/2. Okay, so I'm going to take this opportunity to give you another example of how to solve this problem. So I'm going to solve this problem twice, and this time I'm going to use slightly different, do it slightly differently. So note there that we had to change the variables. Another way we could do it is we could just take the indefinite integral first and plug everything in later. So if you take the integral, and so I'm going to do the indefinite integral here. So someone asked earlier, is the integral from minus infinity to infinity just the indefinite integral? No, it's not. And this is going to give you an example of why. So x over x squared plus 1 squared dx. Well, this is going to be equal to, well, we still use the same U-substitution, but we don't have to worry about the limits now. So this is 1 over 2 times over u squared du, which is going to be equal to 1/2 times minus 1 over u plus c. Of course, since this is the indefinite integral, we still have to have this plus c. And we can plug u back in now. So this is equal to minus 1 over 2 times x squared plus 1 plus c. Okay, so we could also do it using the indefinite integral, and then we can plug it back into the definite integral. So then the limit as a goes to minus infinity of the integral from a to 0 of x over x squared plus 1 squared dx. Well, that's just equal to the limit as a goes to minus infinity of, well, we know what the indefinite integral is, so you can just plug that in. Minus 1 over 2 times x squared plus 1 from x is equal to a to x is equal to 0. Well, this is the limit as a goes to minus infinity of minus 1/2, because when you plug in x is equal to 0, you just get minus 1/2, plus 1 over 2 times a squared plus 1, and so this is still equal to minus 1/2. Okay, so note, we did this a couple different ways. One way is we did the change of variables on the definite integral, and then we need to change the limits as well. The other way is we can just do the U-substitution on the indefinite integral to get the antiderivative, and then we can use the fact that's an antiderivative and plug that in directly without changing the limits for x in the second step. Does that make sense? So whenever you're doing these sorts of U-substitutions or integration by parts, you can also just do it for the indefinite integral and then plug everything in at the end. And some of you may find that easier than keeping track of like which limits go where. So both of these are options, and they both will always work. Okay, so but this only gives us the first half, right? So now, what about the second half here? Yes, exactly. So Ken asked the question, what happens to the integral from 0 to plus infinity? Well, we haven't solved for that yet. So let's do that in the second half. So let me continue this example. And let me just copy the integral down. So the integral from 0 to infinity of x over x squared plus 1 squared dx. Well, so now you can do a couple different things. So note that this is still the same integrand. And so you can use the same U-substitution. So you know that this is u is equal to x squared plus 1, du is equal to 2x dx. In fact, you don't even have to repeat this, because you already solved for the indefinite integral, right? But I'm going to repeat it again just so that everyone is entirely clear. So this is equal to the limit as b goes to infinity of the integral from 0 to b of x over x squared plus 1 squared dx. So that's equal to the limit as b goes to infinity of the integral from 0, so we're changing the limits because we're changing the variable here. This is 1 to b squared plus 1 of 1/2 over u squared du. So this is equal to the limit as b goes to infinity of 1/2 times minus 1 over u again, for u equal 1 to u equal to b squared plus 1. And this is equal to the limit as b goes to infinity of minus 1/2 times 1 over b squared plus 1 plus 1/2, which is equal to 1/2 because the left-hand side, this thing here goes to 0 as b goes to infinity. And putting that all together, we end up getting that the integral from minus infinity to infinity of x over x squared plus 1 squared dx is equal to minus 1/2 plus 1/2, so that's all equal to 0. Now, if you were super clever, you might have noticed that you were doing that this is an odd function and that this would happen, but we're not going to worry too much about that. It turns out there are good reasons why these things cancel out, which we're not going to discuss too much today because it won't generally be the case that these things cancel out so easily. The other thing you could have done is note that we had already figured out what the indefinite integral was. So you could have also just plugged in these new limits into the indefinite integral and you would have found the same thing. So using the second half there. So sometimes if you're doing these sorts of things, it's easier to do the indefinite integral first and then plug in the limits later, rather than repeating the process with these different changes of variables. But that'll just depend on the nature of the problem, and both of them will get you to the right answer. Okay, so now we've done that, I'm going to have you all try it out. So I'm going to ask you for both of these. Let's start with the first one. Let me reset my poll here. What is the integral from 0 to infinity of e to the minus x dx? And I'll give you a moment. Oh, sorry about that. Yeah, so it looks like, yes, yeah, sorry about that. Yes, so it looks like some people think it's convergent and some people think it's divergent, with most people thinking that it's divergent. So let's work this through and see whether or not it's convergent or divergent, and then we'll know what the actual answer is. So what are we doing? This is equal to the limit as b goes to infinity of the integral from 0 to b e to the minus x dx, which is equal to the limit as b goes to infinity. Oh, it looks like we got a sudden flurry of a's near the end, but well, we'll see. Let's see what will happen. B goes to infinity of, well, what is this? This is minus e to the minus x from 0 to b. Well, that's equal to the limit as b goes to infinity of minus e to the minus b plus 1. Which is going to be equal to 1 actually, because e to the minus infinity. Well, if you take e to the minus infinity, that's going to go towards to 0, and therefore this is actually convergent. Okay, and this is because limit as b goes to infinity of e to the minus b is equal to 0. Okay. Let's try another one. So let's try another one. And let me reset my chat here. What about e to the x dx? And we're going to go from minus infinity all the way to positive infinity. Okay, so we have a lot of guesses that it's going to be divergent again. Well, we'll see if that's correct. Okay, so it seems like we actually have a bit of a mix here. Minus infinity to positive infinity, and did I reset this time? Maybe I forgot to reset. Oh well, it's not that big a deal. Let's work this out and see what happens. So this is equal to, so the integral from minus infinity to 0, e to the x dx, plus the integral from 0 to infinity of e to the x dx. I am going to so I'm going to be a little bit notationally sloppy here and not write out all the different limits, because writing out limit every time is a little bit time-consuming. So instead, I'm just going to write out, abuse notation a little bit, and say that this is equal to e to the x from 0 to infinity, because the integral of e to the x is just e to the x. So that is equal to e to the infinity minus e to the 0, which is equal to, well, infinity minus 1. And what's infinity minus 1? That is infinity. So yes, you guys are correct. So this is the divergent. Okay, so hopefully that gives you a sense of how these things work. You take the integral from time 0 to infinity by just taking this limit. And then you plug in infinity in for b or for a, depending on whether you're going to positive infinity or minus infinity. And then you take these limits, and that'll tell you whether or not the the improper integral is convergent or divergent, and also give you an actual answer in the case when it's convergent. Now, you might be asking, why do we care about all these infinities? We already have one infinity in the shape of getting the super tiny, like triangle, rectangular slices. Why do we care about integrating all the way to infinity? If you think about it, in most applications, you're only interested in some finite amount of time, right? Or some finite distance. You're not actually going to go off to infinity in the real application. But it turns out there are some examples where you are going to go on to infinity. One of these is radioactive decay. So now, plutonium-238 has a half-life of 87.7 years. Suppose you have a sample plutonium that releases 100 rem per year. So this is a measure of radioactivity. So how much total rems of radioactivity is emitted by the sample over eternity? So it turns out that the radioactive decay, well, there's some chance that half-life of 87 years means that over 87 years, half of your plutonium decays. And over the next 87 years, another half of your plutonium decays unto infinity. And so you do actually have to integrate all the way to infinity to figure out the total amount of radioactive decay. So this is a little bit more complicated of a problem because I have several different pieces here. One is this idea of half-life, which we haven't really discussed so much, but it's basically the amount of time it takes for something to get to 1/2 of the original amount. So let's start with that, radioactive decay. And it turns out that there is a formula for this sort of radioactive decay, which I'm just going to give you, or give us, since this is a problem we're going to be working through together. So P of t is going to be equal to the amount P of 0 times e to the minus kt, where k is some constant. And P is the amount of plutonium that you have. Okay? So what we want is there to be 1/2 of the original amount of plutonium. And so if P of 0 is the original amount of plutonium, you want 1/2 P of 0 is equal to P of 0 e to the minus kt. And we know that this is the amount of time it takes for it to get to 1/2 is equal to 87.7. So 87.7 k, and we want to solve for this constant of decay. So when we do this, these cancel out because that's just the original amount, and you're left with minus 87.7 k is equal to natural log of 1/2, and your decay constant is going to be equal to 0.0079. So those of you who are in environmental sciences or biology, at some point you may do a biology lab where you have to measure these sorts of decay constants. I think when I took general chemistry, we did it using a thorium sample, but these are the sorts of things that you have to measure. You want to measure these sorts of decay constants and the amount of radioactivity that's coming out of particular samples. And this is the math behind figuring out these decay constants. So now, the next thing we want to do is we want to figure out how many REMs are released. So how much radioactivity is released. So if you want the amount of REMs released, well, this is some integral from 0 to infinity of your original amount times some rate constant r dt times dt, where r is a rate of REMs released per unit of plutonium. And we know that P of 0 times R is equal to 100. 100 rem per year. Okay, so now we take the integral, and what we're going to get is this is going to be the integral from 0 to infinity of P of 0 times R times e to the minus kt dt. And that's because P of t is just equal to P of 0 times e to the minus kt minus kt. And so that's equal to the integral from 0 to infinity, because this thing here is just equal to 100. 100 e to the minus kt dt, which is equal to minus 1 over k times 100 e to the minus kt from 0 to infinity. So this is going to be the limit as b goes to infinity of minus 100 over k times minus 1 plus e to the minus pk. And we know what k is because we solved for that, and this turns out to be equal to just 100 over k. And so this is going to release a total of 12,658 REMs over eternity. So we have some amount of plutonium over the lifespan of the universe. It's going to release 12,658 REMs. Okay, does anyone have any questions about that? So the basic idea here is there are these applications where you have to integrate to infinity, even in real-life biology and chemistry, usually to deal with these sorts of decay-type problems. And you might notice that this is a convergent integral. And that makes sense, right? Because you know that as your plutonium decays, you have less of it. And you only started out with a finite amount of plutonium, and so clearly there's only a finite amount of that can decay, and so over time you're going to have a convergent integral of how much total radiation that sample is going to release before it's completely decayed. Okay, and let's give a couple more mathematical asides. One of them is you guys should know L'Hopital's rule, which is basically, I'm not going to go into this in detail because it should have been something you studied in Calculus 1, but it is something you might want to keep in mind because you want to know how quickly different things go to 0 or to infinity. And so if you have a limit of f of x over g of x, so if you have a ratio of two different things, then if both of those are 0 or both of those are infinity, well, then you can use L'Hopital's rule and take the derivative of both f and g to get the limit. So, for example, something like, let's see, I'll give an example in a moment. One useful lemma is if r is greater than 0 and n is any number, the limit as x goes to infinity of x to the n e to the minus rx is going to be equal to 0. So basically, all we're saying is that exponentials grow faster than polynomials. And this is going to be the primary use of this, because sometimes you're going to have to do an improper integral, and you're going to have something that ends up being like x over e to the x, and you need to know that as x goes to infinity, or as b goes to infinity, or whatever, that entire thing goes to 0 instead of infinity. And so this allows you to compare the two different quantities. So let's go ahead and work through another example where we make use of that. So this is going to make use of all the different things we've learned in this course. So the first thing is x e to the minus x dx. How do we take the integral of that? Does anyone want to put in chat what do you think we need to do? This is not for credit, for the record, but it would be nice if someone mentions, okay, so we have some guesses of U-substitution and integration by parts. So now the problem here is it turns out that U-substitution won't work so well because what are you going to use for your U? If you use U, x is equal to U, then you don't actually make any progress. If you use U is equal to e to the minus x, well, the derivative of that is e to the minus x, is minus e to the minus x dx, and so it doesn't make progress. But if you use integration by parts, note that we haven't. So remember, we had our acronym detail, and we have a exponential part here, and we have a algebraic part here. Okay, so we can use integration by parts. And we're going to do this by solving the antiderivative first. So let's do it by first solving for the form without the limits. And then we can plug in the limits later. So let's say that u is equal to x, so du is equal to dx. And we have dv is going to be equal to e to the minus x dx. Luckily, it's an exponential, and exponentials are easy to take the integral of. So v is equal to minus e to the minus x. And this allows us to solve this. So remember, it's the integral of u dv is equal to uv minus the integral of v du. So that's the general form of integration by parts. So this is going to be equal, well, what's uv? So that's going to be minus x e to the minus x minus the integral. Well, what's v du? Well, that's going to be minus e to the minus x times dx. It turns out that both of these minus signs are going to cancel out. So this is going to be equal to minus x e to the minus x minus e to the minus x, because that's the integral of that, plus some constant. And we can plug this back in. So that means that the integral from 0 to infinity of x e to the minus x dx is going to be the limit as b goes to infinity of minus x e to the minus x minus e to the minus x from 0 to b, which is going to be equal to the limit as b goes to infinity. Let's plug it all in. So the first part is plugging in b is going to be minus b e to the minus b minus e to the minus b minus, when you plug in 0, that's going to be 0 minus 1. And it turns out that, well, e to the minus b is going to go to, as b goes to infinity, goes to 0. So this goes to 0, that goes to 0. This already is 0. And so this entire thing is just equal to 1. Okay, so note that here we combine together a bunch of the different things we learned. So we solved for the antiderivative, then we used the fundamental theorem of calculus to relate the antiderivative to the definite integral. Then we plugged in the limit as b goes to infinity of this definite integral. And then what we ended up with is we cancel out a bunch of things using L'Hopital's rule, because e to the minus b goes to 0 faster than b goes to infinity. And then you're left with just 1 for this complicated looking integral from 0 to infinity. Okay, let's do a bit more of, so let's do a quick review. So this sort of ends the first 2 weeks of this course, and you guys have learned a ton of integration rules. So the first thing you guys learned is, well, there's this idea that this definite integral is just this Riemann sum of a bunch of different rectangles. You also learned that you can combine together these Riemann sums, so integral from a to b plus the integral from b to c is just the integral from a to c. Or if you have integrals from the same regions, you can just add those together. So integral of f of x plus g of x is equal to integral of f plus g. And of course, this is all just area under the curve. So that's super important. That's one of the main applications. And then we have the fundamental theorem of calculus, which relates together these antiderivatives with these definite integrals. And I think I left out a dx layer. Sorry about that. And then we also have the technique of U-substitution. So it's sort of weirdly written here, but basically what you can do is you can plug in U so long as you also plug in du. And we had integration by parts, which is just covered, as well as the mnemonic for trying to guess which part should be U and which part should be dv. And then we also studied volumes of revolution, but just in general, volume is the integral of these area slices. And that sort of ends the integration part of this lecture. I'm going to give you guys another 5-minute break, and then we're going to come back and start working a little bit. Oh, sorry, yes, if you have any questions, now is the time to ask them. Because after the break, we will be getting a brief preview of some of the linear algebra part of this course. But yeah, so this is the previous slide. We used integration by parts, and then we did this improper integral by taking limits. Does anyone have any questions right now? This would be a great time for you to ask questions about the integration, about the sort of basic integration part of the course. This lecture is also on the quiz. Yes, everything up to this point is on the quiz. So we have just now ended the material that will be on the quiz next Wednesday and Thursday. Okay, so I'm going to stop my recording and take a brief break.